Let's recall for a second what is integration by parts. It's a way to integrate the product of two functions. One is fx and the other one is the derivative of the function g. And then we get f times g minus the integral of g times the derivative of f. As we already agree, we are really not going to use exactly f and g with integration by parts, but we are going to use u and v. So gx is the v, g prime x dx is dv, and f of x is u, and f prime x dx is d of u. So we are talking here about functions and their differentials. The integral of u dv equals uv minus the integral of v du. As I promised you in part 1, here is an example of integration by part of inverse trigonometric function. All inverse trigonometric functions are done by integration by parts. Because I cannot integrate this one, I must differentiate that. So this is going to be the u. I have no choice but to take u to be the arcsine of x. So the du is dx over a radical of 1 minus x to the power of 2. But also now I have no choice but to take dv to be dx, so v is x. In the setup of the by parts, I get x arcsine of x minus the integral of v du, which is the integral of x over square root of 1 minus x to the power of 2 dx. This one, it's an easy u substitution, but I don't want to use a u substitution now because the u is the arcsine of x, so I'm going to call it w substitution. W is 1 minus x to the power of 2, and this is the w. And because in the integral I have only x dx, I do a little bit manipulation here and I get that x dx is negative dw over 2. So I have a constant of negative 1/2. The first part, it's always, you just copy that because there is nothing to do. And the second one, okay, we are going to use the w substitution, and you can see that I can use now the power rule because this is an integral of w to the power of negative half. So when you add 1, you get a half, and that's why you get this one. You can cancel out the 1/2 in the second part, and you get that. The only thing left to do is to get rid of w and replace it by 1 minus x to the power of 2, and I get the answer. Another example, the integral of x to the power of 2 e to the power of 3x dx. You can recognize the loopy e to the 3x, and you should recognize the reduction x to the power of 2. So this is a clear cut of u equals x to the power of 2. So du is 2x dx, and dv is e to the 3x dx. So v is e3x over 3. Okay, don't forget the little u substitution when you do that. To get v, you're actually finding the antiderivative of e to the 3x dx, so you actually have to do here a u substitution, or I can call it w substitution, when w equals 3x. So here is the setup. Now you can see that I still have to work this out, so I'm going to do by parts again. U now equals x, so du is dx. dv is exactly as before, so v is exactly as before. So again, you have to be very, very picky about your algebra. Okay. Brackets, parentheses, use all that. And we get that. Okay, so now I'm doing again the integral of e to the 3x dx, and I get that this is e to the 3x over 3. So because I have 1 over 3 before, I get 1 over 9 times e to the 3x now. Well, we can simplify this a little bit because you can see all of those terms have e to the 3x and over 3. So we can distribute e to the 3x over 3, and we get that. Again, I would like to remind you that even though it takes so much time to integrate those functions, it's very easy to check by differentiation that this is really right. You just have to take the solution, differentiate, and you should get your integrand. Example, the integral of x to the power of 2 ln of x dx between 1 and 3. Okay, pay attention. We just did one problem and we had there x to the power of 2 e to the power of 3x dx, and we chose the x to the power of 2 to be the u because we got reduction. But here I really don't care about the reduction of x to the power of 2 because I have a bigger problem here. I don't know how to integrate ln of x, and that's why the u has to be now ln of x. So the du is dx over x, and this is dv, and v, you have to take the antiderivative, please do it right, you get x cubed over 3. Because this is a small part in a big problem, I suggest all the time to differentiate v and to see that indeed you get x to the power of 2. So here is the setup of the integration by parts. So don't be alarmed by this integral now, because this is just x to the power of 2 over 3 after cancelling one of the x's in the numerator and the denominator. So this is an easy integral, so we can do it and we get x cubed over 9. So the only thing left to do now is to substitute the limits 3 and 1. And here's what we get. Okay, I would like to recall ln of 1 is 0. That's how we got this 0. And now we can do the algebra. And we get 9 ln of 3 minus 26 over 9. I will have to recall that not all the time a combination of x and ln of x are integration by parts. It's really depend on the integrand and the set. For example, here we have an integral of ln of x to the n over x dx, and as you recall, this was a u substitution when u equals ln of x and du equals dx over x. So just to recall, we got this one, and it was a really very easy integration.